The Department of Chemical Engineering and the ACTEC Alumni Association takes pride in initiating a lecture series under his name. I now invite Dr. K.V. Radha to deliver the welcome address.
A warm welcome to each and every one of you present over here. At the outset, on behalf of the Department of Chemical Engineering, I invite our esteemed chief guest of today, the presenter, Sir Ramchandran sir. I welcome you on behalf of the department. And I welcome the ACTA members, Ms. Vidya ma'am, Sugma Devata sir, and all those present on and off the dais, and our dear faculty members and our students. A very warm welcome. And today it is going to be the beginning of Dr. GSL Lecture series, which is going to give you a pivotal role for your upliftment on education. Actually, this Dr. GSL series started for the benefit of the students of Chemical Engineering Department, where you will be able to hear from the experts. It's not just a matter of 3 to 4 years who had been working on it, 30 to 40 years of experience and subject expertise, which you will be hearing, and mostly from the industrial arena, where they have worked in and out of any processes. The all technical details, whatever they have gained throughout their life, the experience in and out of the projects, what they have worked on. These are the things you will be learning throughout these lecture series. As you all are more towards AI and other systems of knowledge, but the basic knowledge of a chemical engineer lies on the conceptual basis. Your basic mathematics combined with chemistry, biology, physics is going to be there with you if at all you want to shine in your way of life, wherever you're going to take path for. See, now even Elon Musk has already defined, all people cannot compete now with machines. We have to have our basic conceptual thinking, the reasoning, the idea, which cannot be brought out by AI or ChatGPT, whatever it is. So we have to linger on to our basics. Through our basics, you can compete with the AI. Through your logical thinking, reasoning, thinking capacity, other ideas which you are going to put forth in any industry which you are going to place for, there you are going to shine. So, in order to shine there, you need to have the idea what the experts are going to tell you. Take each and everything. If at all you brought in your notebooks, please note it down, because these type of expertise ideas you can never come across. See, each and everything you cannot pass on the hurdle each and every time. What they have passed on, how they have come out. These are the things we need to know about. So our experts who are going to talk in this lecture series over the period of years, right from this day, please be part of it and take notes whenever and wherever it is required, and come out of your, and then ask questions, whatever the doubts may be. Today our chief guest is going to talk about soda ash. Means what is that? You're going to talk about soda ash. Where are the raw materials coming from? This is where a chemical engineer's actually role is playing now. It is right from the raw materials to the end product. Everything comes into picture, because you are the only branch of engineers who actually design the entire industry when you're going to come out as after your 8th semester. So your role is a global impact. So your thinking, reasoning will definitely uplift globally. So with this small few words, I thank each and every one of you, like ACTA members and our chief guest, along with everyone, our faculty members, everyone who have really put in their breath in and out to you for your upliftment. So thank you and welcome you all once again.
Was brainstormed a few weeks ago, and I must mention the support and contribution given by Mr. Ramachandran, who is seated in the first row, and Dr. Radha, who together designed what is needed utmost for the students of chemical engineering. I have just two lines to say. One is that you have the greatest benefit of reinvesting your time and effort in making this college go back in time when titans were here, like Dr. GS Ladha. Many of you would have seen him only in photographs. We have all seen him walk and talk and be silent. His body language spoke, his look spoke, his limited words spoke. There used to be an aura around him of fear and respect. That was what was Dr. G.S. Ladha giving to this college. Such a level of knowledge and wisdom and such love for students. You are going to listen to experts who have been contributing to the industry. And the second thing which I would like to say is chemical engineers, as Dr. Radha clearly mentioned, have the biggest advantage of having a synthesis of all the engineering subjects and all the science subjects, unlike other divisions. And this is going to give you some power which will awaken something in you to bring out the best in you. So make the best use of all of these. Do not even miss one of them. Each speaker will be handpicked by the department as well as the group who is involved. And they are going to be contributing to the college, bringing in collaborations and cooperations between the industry, which was, something that AC Tech was always known for. And I'm really happy to be a part of the group that is planning these series. And I wish the function and the event and the presentation the very best. And as Dr. Radha said, please take down notes, because these are some things which, you never get. So even after leaving the leaving the college nearly 40 years now, I'm going to be taking notes. So that's the thing that we all want to have as a wonderful memory, long-term core memory of such events like this. Thank you very much.
Thank you, ma'am. I'm sure this lecture series will be of immense usefulness. Vidya Shankar ma'am, giving a memento to our chief guest.
Good morning, everyone. It is my great honor and privilege to introduce our esteemed chief guest and speaker for the day, Mr. G. Ramachandran, who has graciously accepted our invitation to give a lecture on soda ash manufacturing, its perspectives. Mr. G. Ramachandran is a chemical engineer and obtained his B.Tech degree with distinction from Regional Engineering College, now National Institute of Technology, Trichy, Tamil Nadu, in the year 1973. Later, he to Tuticorin Alkali Chemicals, where he was the managing director for 12 years. He was earlier with Manali Petrochemicals, a company promoted by SPIC, for 25 years, starting as project manager and held the post of managing director for 11 years. He started his career as a management trainee in SPIC and has held various positions in technical and marketing functions. He has wide experience in designing, erection and commissioning of petrochemical and fertilizer plants. Mr. Ramachandran worked in the commissioning team of fertilizer plants for NFL and ICI. He has design experience of plants by association with projects in SPIC, TFL and ICI. Mr. Ramachandran was actively involved in the turnaround of the companies like TFL, MFL, and was instrumental in the implementation of the project to separate carbon dioxide from boiler flue gas at TFL, which is the feedstock in the manufacture of soda ash. May I now request Mr. A. Ramachandran to kindly come forward and give a brief introduction about the lecture on soda ash manufacturing, its perspectives. Thank you.
So I am starting now. Soda ash before chemically manufactured in Egypt from wood tree root ashes, seaweeds and urine is used. French king and French Chemical Society announced the award to invent the manufacture of soda ash. The Lebanon reactor sulfuric acid is sodium chloride, produce HCl and sodium sulfate. This HCl presence of copper converted to chlorine used in bleaching powder, calcium hypochlorite, and sodium sulfate with coal, dust, calcium carbonate in furnace burned. So sodium carbonate and calcium sulfide is produced. Calcium sulfide converted to hydrogen sulfide used as a raw material to produce sulfuric acid by lead chamber process. Later, Belgium invented in Solvay process where ammonia, calcium carbonate, sodium chloride is the raw material. Actually, a very interesting chemical thinking. Calcium carbonate and sodium chloride cannot react. So ammonium hydroxide is introduced, recycled in Solvay process and dual process ammonium chloride is precipitated. So fresh ammonia is used in dual process. Speak supplied carbon dioxide, ammonia to TAC and some extent carbon dioxide from flue gas is extracted, thereby emission of carbon dioxide is reduced to atmosphere. In organic chemicals, maximum chemical produced is sulfuric acid followed by sodium hydroxide and sodium carbonate. Actually, Tata GSL Nirma capacity is very much more than TAC capacity, so they are able to sell at Tuticorin at the same rate of TAC. Further, from Bulgaria, Solvay product is coming to Tamil Nadu, around 2,000 tons per month. Its selling price is almost same of TAC. The sea freight from Bulgaria port to Chennai port is around 5,000 rupees per ton, but lorry freight from Mithapur, Tata Chemical to Chennai is also 5,000 per ton. Further, natural gas magadi is available in Kenya of low purity. Tata Chemicals also mines in Kenya. Due to development technologies, detergents invented by Henkel in 1931 and Procter & Gamble invented in 1932. Then enzymes by BSF around 2000. BSF is the largest chemical company in the world. Ammonia eBay process got Nobel Prize for chemistry, and the scientists also worked for BSF. So the cost of production by Solvay and dual process for various capacities and capital expense in Solvay process to recycle ammonia and dual process for crystallization of ammonium chloride is not known to me. But the calcium chloride byproduct in Solvay process is commercial value is less than the dual process byproduct ammonium chloride used as fertilizer. Thank you.
The grades H, D plus, D plus, etc. Usually you find your seat in REC. So in REC I went there, I found a queue there. Then they said this queue is for people who are interested in writing, joining chemical engineering, because that was the second year of chemical engineering. So I also stood in the queue, wrote the entrance exam. By evening I was admitted in chemical engineering. So when AC Tech announced their results, I could not get back because our principal took the initiative of, you won't believe, convincing my father to continue in REC. So anyway, I had good friends in AC Tech, and also we had good teachers from AC Tech teaching in REC, and later from REC they came back here. I think, remember Dr. Krishna Swami, who taught us physical chemistry. Anyway, we go into the talk today. As I told you, I worked in Tuticorin Alkali Chemicals nearly for 14 years, but as a Providence, I also worked in the basic design in 1978 by accident for about a year. we completed the engineering, and after that, the TAC had its own team. So I was continuing the petrochemical division in the projects department of SPIC. So this company was set up, was conceived by the founding fathers of SPIC way back in 1969 itself as contiguous to SPIC plant. SPIC plant is at that time was the world's largest ammonia and urea plants. Single stream urea plant, 1600 tons per day was the design capacity. So they had excess carbon dioxide. So instead of wasting it, they thought of this soda ash plant, dual technology, which was not operating anywhere outside of Japan at that time. Even in Japan, there was only one plant. So now going to, so the next slide is, so we will talk about the soda ash manufacture briefly. Probably will expose you to the what is the process that is followed briefly, and about how we implemented a carbon dioxide recovery plant to recover carbon dioxide, which is the raw material, from the flue gas of the boiler, which is producing steam for the process. And we also produced for the first time in the world, and still we are the only one in the world to have produced the green soda ash for Messrs. Hindustan Lever. And I will also tell you about briefly about the green ammonia and how we produced water by innovative method by the RO process from the seawater. So TFL is the only soda ash manufacturer in the world operating with the recovered carbon dioxide gas, and that too from a biomass fired traveling rate boiler, fully fixing all the carbon dioxide in the flue gas to approximately 100,000 tons of soda ash. So we produce this plant, CO2 plant, what we produce can recover 65,000 tons of CO2 in a year. So Hindustan Lever, who are interested in reducing the carbon footprint of their soda ash, of their detergents, because they have already announced that by 2030 they would like to eliminate 90% of the carbon footprint. So they really appreciated our efforts, and then gave us an award, gave TFL an award as the Business Partner of the Year. And even though we did all these things, we have not received any special benefits or credit for the initiative of the company. Why is after seeing this slide, I will explain to you why we went for the CO2 plant. This was SPIC was promoted contiguous. The soda ash plant was contiguous to SPIC. The technology adopted is that of Toyo soda, and it is called eco-friendly dual process. I will explain to you later why it is called eco-friendly dual process. It produces soda ash and ammonium chloride as a co-product, almost nil effluent. Whereas in a conventional soda ash plant, 99% of the calcium chloride effluent is pumped into the sea. Okay, it is too difficult to recover so much of calcium chloride because there is no market at all for the calcium chloride, and the cost of production of calcium chloride is usually more than the selling price of calcium chloride. So unless and until you have excess energy available, no point in setting up a calcium chloride plant, and that to recover from a dilute solution in a soda ash plant. So why they set up this plant in Tuticorin is CO2 gas and ammonia are available from SPIC at that time, and locally salt is a major raw material, and it is available plenty in Tuticorin at that time. Now of course TAC is also getting shiploads of salt from Gujarat because vagaries of weather in Tuticorin has affected the salt production. So the basic process, I would like to deviate from whatever Mr. Ramchandran has introduced you in his introduction. Nowadays the process is very, very simple. So the ammonia and water, they react because they have affinity 500 times, as you have studied in your chemical classes. So they produce ammonium hydroxide. This ammonium hydroxide reacts with carbon dioxide to produce ammonium bicarbonate. Ammonium bicarbonate double decomposed with sodium chloride to produce sodium bicarbonate and ammonium chloride fertilizer. This ammonium chloride fertilizer is usually destroyed using milk of lime, that is calcium hydroxide, to liberate the ammonia back, and that is used back in the process. And it produces calcium chloride as an effluent which is pumped. This ammonium bicarbonate double decomposed to actually produce sodium bicarbonate, which is calcined to get you sodium carbonate. Whereas in a dual process, we don't destroy this ammonium chloride. Since it is also in a dilute solution form, it is crystallized, and with the common ion effect of using the solubility difference between sodium chloride and ammonium chloride, we sort out this ammonium chloride, centrifuged out and dried, and then it looks like same like urea, which is the fertilizer used by the farmers regularly all over India today. And this ammonium chloride unfortunately has got only 25% nitrogen, whereas urea has got 46% nitrogen. And we cannot fight the price of urea, which is subsidized by government of India, with this 25% nitrogen ammonium chloride. And that is the primary reason for this company not coming up, because there was no government subsidy or support in the production and marketing of ammonium chloride, even though it is a fantastic fertilizer for certain type of soils and certain crops which enhances the oil recovery. So bulk of it we were exporting to Malaysia and Indonesia, where it was going for palm, since it enhances the oil in the palm trees, palm fruits. So this we have already seen. Salt is locally available. CO2 gas was available almost free because they were venting it to the atmosphere, and ammonia. This ammonium chloride fertilizer, since SPIC is already a fertilizer company, they thought it's easy to market this product. So this was the genesis of this product. But we faced a lot of issues. This company, right from inception, faced a lot of issues. Like first one, SPIC, even though it was designed for 1600 tons of urea, and what we found is even in the first week of operation, we could raise the load up to 1850 tons. Okay, slowly. Even in fact, I remember the Japanese coming and telling me, we cannot produce more than 1600 tons. But even the very first day, we produced the 1640, and then it went up to 1850, and currently it is producing 2050 by further debottlenecking. And they are working on projects to further increase the production to 2500. Why I am saying this is, the CO2 gas, what was available as excess free, was no more available to TAC. So TAC was always, that is Tuticorin Alkali Chemicals, always was at the receiving end. They could not get the CO2, enough CO2, because SPIC has to maximize the production as per the Government of India and Fertilizer Ministry. So this company suffered for want of ammonia and want of CO2. But luckily in 1982, SPIC set up an importation terminal in the Tuticorin harbour. So one problem was solved. The required ammonia was continuously imported, whereas still the CO2 gas was in short supply, and they were always at 50% load. They could not go beyond 50% unless and until SPIC reduces their urea plant load and give them more CO2. So another dimension to the problem is Government of India took a decision that they will switch to gas reforming. All the fertilizer plants throughout India, they switched to gas reforming instead of naphtha reforming, because at that time gas price was much lower compared to naphtha. So we started exporting naphtha from India and importing gas, and also we stuck gas in the Bombay High, and most of the plants in the northern belt, they had the privilege of getting this gas, whereas the three plants in India, that is Madras Fertilizers, Tuticorin and Mangalore, didn't have access to the gas. So these plants remained shut down for 4 years for want of gas. Both SPIC and MFL and Mangalore fertilizers, they became almost sick because of they were out of operation for 4 years for want of gas. So now gas is available because we are importing gas, and also gas mains are connected to Ramanathapuram field, and from Ramanathapuram field we have taken the initiative to lay that 100-kilometer long pipeline. So now we have gas available, and SPIC has completely switched to gas reforming instead of naphtha reforming. Naphtha, as you know, it is in the homologue, it is somewhere in C5, C6 area. Okay, so the carbon hydrogen ratio is much higher. So you produce more CO2 for the same amount of hydrogen that we reform. Whereas in gas reforming, C by H, as you know, it is only 4, right? It is predominantly methane. So C by H ratio is only 4, and so they produce for more hydrogen and less of CO2. When you reform 1 mole of natural gas, you produce more of hydrogen and less of carbon dioxide. So SPIC itself is suffering because they are not able to get the required CO2 required for producing their ambitious target of 2,500 tons of CO2, urea. So I will explain that how they solved the problem now. So the lower capacity utilization led to very great losses in TFL, and TFL was sick and was in the BIFR, that is Bureau of Indian for what is it called, the rehabilitation of these kind of sick plants. But none of the plants came out successfully of that thing, and I'm happy to say that TFL is the only plant in the whole country to come out of BIFR and then successfully operating now. So TAC needed more carbon dioxide gas to increase the carbon dioxide production. To increase the soda ash production, because if the capacity utilization goes up, then we can produce more of soda ash. And as Mr. Ramchandran said, we have no competitors because all the soda ash plants in India are in Gujarat, excepting the one in Tuticorin what we have. Why they are in Gujarat is because they have both lime and salt available, and all of them follow Solvay, and they pump the effluent into the sea. That was the easiest topography that you can set up a soda ash plant. Whereas in Tuticorin, we cannot pump the effluent into the sea because it is a sensitive fishing harbor. So no effluent can be pumped into the sea even if it is treated. So we set up this dual technology plant where ammonium chloride is not destroyed and it is recovered as a fertilizer. So the carbon dioxide sourcing, what we have to do is we set up 2-3 pilot plants, one after another. In the last 15 years, TAC has been studying. In fact, they have spent a lot of money in setting up. First one was, the very successful one was ammonia brine, chilled ammonia brine. We operated 4 degrees, so you absorb the flue gas and ammonia, we produce ammonium bicarbonate. So ammonium bicarbonate is heated and then the carbon dioxide is got back. It successfully ran, but it has very, very difficult situations because you cannot maintain the ammonium bicarbonate, ammonium carbonate ratio. So if it goes to ammonium carbonate, then the amount of energy that is required to break it, to bring it back to CO2 and ammonia independently is very difficult. So we gave up because of the energy requirement, because the cost of power in Tamil Nadu was very high at that time. Even though now it is almost same as more or less all the states, but at the time Tamil Nadu is the highest. So we gave up that project even though it ran successfully. So we even thought of lime kiln and export the lime and use the carbon dioxide. But since that highly dusty plant and the limestone has to be imported because we need a high purity lime. So the CO2 absorption, including using milk of lime, was also tried. Even though it works very well, but it involves too many operations to recover the CO2. So finally, we experimented on the laboratory scale with different type of amines. At that time, we came to know, with the help of one of the technical leaders who are working with Reliance, that two young graduates in IIT Bombay, they are working on categorizing various amines about their absorption capability. In fact, they completed the project and they got their MTech degree. So I got in touch with them, and then with the help of basic engineering company in Chennai, whatever they developed it as a MTech project, we converted it into a basic engineering design and detailed it out, and then constructed our own plant. First, we tried it out in the pilot plant, which was working all right. So then we scaled it up and made it into this plant. So to give you an example of the record, had we gone to people like Mitsubishi, who have successful 12 plants at that time in the world, and India itself had 4 CO2 recovery plant at that time with Mitsubishi's technology. This plant would have costed at 122 crores, whereas we built it in 21 crores. So with our own design, and all the equipments are made in Chennai and Tuticorin, and the plant is operating successfully, and it has helped the company to completely turn around, because we were able to produce the CO2. At that time, the boiler was working with carbon dioxide, with coal as the fuel. Whereas since Hindustan Lever wanted us to reduce the carbon footprint, we switched over to biomass fuel. So first we experimented 20%, 50%, then finally went to 100% biomass. Now currently it is working on 100% biomass. The carbon footprint came down by 0.6 tons per ton of soda ash, so which is a dramatic reduction compared to the Solvay process. Solvay process, for example, it is around 2.8 or something is the carbon footprint, whereas in dual process it is already 2.12. Now it has come down to 1.6, and by switching to biomass fuel and also switching to green energy, we completely reduce the carbon footprint around 0.4 now. Okay, so that means the detergent what Hindustan Lever produces with the soda ash produced in this process is already green, but still they want us to make it negative, because it can help them in reducing the overall carbon footprint of the detergent. So for that we have to use green ammonia. Green ammonia is produced using green energy, that is solar and wind, and only electrolyze the water, so get the hydrogen, and then the hydrogen will be converted into ammonia. So since we have excess capacity in the ammonia plant, so we are using this green hydrogen. Project is on, is still not complete. Using this hydrogen, it will be converted into green ammonia. Green nitrogen will be produced again with an independent cold box by liquefying the air. The power for this will come from wind and solar, and we are co-working with Singapore company who have set up plants in Rajasthan and also in Vattambalim near Tuticorin itself. So this green ammonia, now they are setting up a large plant itself to produce approximately 300 tons of ammonia per day. Okay, coming back to soda ash. So far I have covered why we went for carbon dioxide recovery and how to produce soda ash. Now you see in this picture, you see this one is the soda ash plant, and this one is the carbonation towers, and this is the ammonium chloride bagging section. Okay, so what are the uses of this soda ash? Different grades of soda ash are there, but we produce sodium carbonate and sodium bicarbonate. Sodium bicarbonate usually used in food industry and also for poultry feeds. Different grades of ammonium chlorides are there, that is technical grade and fertilizer grade. And we also added through R&D effort sodium bicarbonate and ammonium bicarbonate plants. So all these things were produced based on the internal effects of the internal team of R&D and plant engineers. We could reduce this. A technical grade plant was really an innovation, but unfortunately now we are not operating it because what we are doing now is converting all the ammonium chloride produced into complex fertilizers in SPIC. That's one of the reasons for the turnaround. So we are not operating ammonium bicarbonate or technical grade ammonium chloride. So these are all the plant capacity. Now the soda ash plant is being expanded. So it is under commissioning. By October end we should be in a position to produce this expanded capacity. For this also we have built another large carbon dioxide recovery plant, the second largest in the world, 1,200 tons per day CO2 plant, gathering all the carbon dioxide, whatever is coming out of the chimneys of the SPIC fertilizer plant. They have 3 boilers operating and a reformer. So reformer flue gas and all are are operating on natural gas. So it is mostly dust free, unlike the biomass fired boiler of Tuticorin alkali chemicals, and they are going for this carbon dioxide plant. The reason for that is since they are expanding their urea plant to 2,500 tons, they need more CO2. So still they will spare 400 tons of CO2 to TAC. So that TAC actually can, including the existing plant, they can produce around 300,000 tons soda ash. So that is existing plant 1,15,000, the new plant 200,000, so 315,000. So the application is pending with the government. So hopefully we will get that clearance, and then TAC can produce nearly 315,000 tons of soda ash. That will make them still it is compared to the capacity of what Tatas have or GHCL or Gaddi, who have built a new plant. This is very less because all their plants are 800 to 1,200 tons per day. But still, in this process, we can be very happy to say that we will be using a required carbon dioxide and also hardly any effluent. And also the expansion plant also is a total deviation from the technology of usual with external coolers, etc. So these plants are developed in China. So this technology now is coming from China, and hopefully I think so this is the first time that is coming to India. So we'll see. We will be to cite an example. The existing carbonation tower produces 75 tons per day. One tower will produce 75 tons per day. How it is produced? From top we send ammonium chloride, sodium chloride and ammonia slurry. Carbon dioxide is pumped from the bottom in 2 different concentrations. High concentration of 90% at the bottom, and in the middle it's around 38%, so that the crystals that are produced are uniform in size. There is no very fast reaction, nucleate reaction, etc. So that the vacuum filters can easily handle. Okay, but whereas in the new plant, each tower will produce 325 tons. So see the capacity, more or less a similar footprint of 3.2 diameter and 24 meter height, but with external coolers, more coolers, etc. So energy removal systems are vast improved in the new technology. Okay, so these are all the raw material requirements for the plant. So I will skip this slide. The next slide may be of interest to you, because here you can see that this is the carbonation section, where from the top ammonium hydroxide descends down, and CO2 gas is sent. Earlier it is used to come from the SPIC ammonia plant. Nowadays we produce our own CO2 from the recovery plant, but still we have the line from CO2. Whenever there is emergency, we can draw the gas from SPIC, but mostly 99.9% it is our own internal gas, and then it goes into the bicarbonate section, and then it is filtered, and the bicarbonate cakes come to calcination section. In calcination section, bicarbonate breaks into carbonates, and then 1 mole of CO2 is released, which is also recovered back and used fully. So this is called light soda ash, LSA, which is used in the manufacture of detergents and also in glass and various uses. We will see briefly what are the uses. And then this can be heptahydrate with addition of water, and then this is called dense ash, so that the density of this ash is close to 1, whereas here the bulk density of the light soda ash will be around 0.6. And TAC is one of the plant which produces the lightest ash in India, and it is most preferred for especially for the spray dried detergents. Okay, in the carbonation section, the filtrate contains ammonium chloride slurry. Usually in solvay process, it directly goes into a distiller where you add the lime, take back the ammonia. Whereas here what it does is it goes into the ammonium chloride plant here. In ammonium chloride plant, we add from the salt is purified, and then the purified and the powdered salt from the ball mill, it is added into the ammonium chloride plant, where the equilibrium between the ammonium chloride and the sodium chloride, in between, if you operate the crystallizer, ammonium chloride crystals come out preferentially. Okay, so then this ammonium chloride crystal is centrifuged out, dried, and then directly bagged. But currently what we do is we bypass the dryer also, and then we send it to the complex fertilizer plant of SPIC directly. And people who are our habitual customers, especially for industrial users in Uttar Pradesh and also in Madhya Pradesh, they are using it for electroplating, etc. Those customers alone, we finish the product and then send it to them as industrial grade. Otherwise, as a fertilizer grade, we have some small belts available in Andhra, where it is used in for the type of soil there, urea will not work. Even ammonium sulfate will not work. So they need an acidic fertilizer. That ammonium chloride is slightly acidic. So they need, for the basic soil conditions, they need ammonium chloride. So we sell there. But predominantly it is converted into complex fertilizer. Okay, uses of soda ash. Bulk is, you will see that it is detergent and glass, and also sodium silicate. Again, sodium silicate goes into detergents. Okay. Then sodium bicarbonate, it is used in poultry feeds and also in biscuits and a little bit in tannery. These are all the various products. I'll skip this slide. The big competitors are, not competitors, they are all very, very big compared to our Tuticorin alkali chemicals. There is Nirma, who have got a very good plant, excellent plant. Gujarat Heavy Chemicals, Tata Chemicals. Tata Chemicals is a multinational now. They have plants in 3 continents. And Gaddi, who came in about 7 years ago. So this, you can see that this is how the installed capacity and production. We definitely import about 100,000 tons, and it is mainly 30-40,000 tons are coming to 3 or 4 ports in India. So mostly it is coming in Bombay. The price wise, if you see, the people, they price the product in such a way that they would like to destabilize the operations in India. Okay, but for the last 7-8 years, they have understood this. The chemistry is working well, so it is more or less at international price. The soda ashes are coming. Only the Chinese people are dumping, so we have anti-dumping duty against China. Otherwise, we still have capacity to put another couple of soda ash plants. which I think will come up because we meet the needs of our neighboring countries like Nepal, Sri Lanka, and even in Pakistan it goes in neutral packing. This is the import export. You can see that we are both importing and exporting. Okay, and sector wise consumption in India, you will find that it is mostly in soaps and detergents and glass. So the brief description about CO2, I have already spoken about the CO2 plant, and it was mostly, this plant was set up not to tell the world that this can be done this way or that way. It is for the sheer survival of TAC. If you have not put up this plant, the plant has to be closed down. What to do with that so much of workmen and then the investment, etc. So in order to recover carbon dioxide and continue the production and continue to be in the business, this initiative was taken, and we commissioned the plant in 2016 successfully, and it is operating continuously, no issues at all. So this has made the plant independent of SPIC. Earlier, if SPIC fertilizer plant shuts down, TAC also has to shut down. And because the India fertilizer industry is that they will give you quota, and once you complete the quota, after that you cannot produce. You have to shut down the plant. So SPIC will complete the quota usually in January itself. So they will shut down the plant in January. So TAC also has to shut down the plant. So we cannot meet the requirements of customers. So all these problems got solved once the CO2 set up. We are totally independent of SPIC. Whether SPIC operates or not, it is not an issue because we are importing ammonia directly. Of course, making use of the facility, which is in the Tuticorin port, and we have the cross-country pipeline right up to the plant. So we switched over to biomass fuel that I have already explained. The CO2 plant is currently operating at 80% because we have deficiency in the soda ash plant because it is very old, and we are replacing some of the major equipments like olden days drum filters, etc. We are switching over to belt filter. Even in the new expansion plant, it's a large belt filter. So those kind of things, once that is achieved, this plant load can be taken up to 100%. So how we produce this is a brief, this one from the boiler, through the back filter, we remove all the dust, coal dust and ash dust, etc. This carbon dioxide gas is cooled first with water in circulation. This cooled gas enters a secondary removal with a carbonate flushing, so that if there is any SO2, NO2 slip, that also will be captured here. This technology alone was developed in-house in our R&D, so that we completely scrub and take out all the SO2 that is present, because SO2 can kill the primary amine that is used in the absorber. Okay, in absorber it is 3 sets of packings are there from tops, 3 sets of packing. So the regenerated amine is sprayed from top, and then it absorbs nearly 90% of the carbon dioxide. But we have seen that it goes up to 95% if you maintain the proper temperature, and we have intermediate coolers also. So we can go up to 95% of the CO2 is captured, and then the amine is water washed, and then the excess oxygen and nitrogen is let into atmosphere. The technology here is usually the primary amines are attacked by oxygen. So most of these projects fail because this amine will be completely killed by this excess oxygen that is present in the flue gas. Because we use up to 15% excess air, that is 5% of the flue gas is oxygen. So these amines are specially stabilized with, that is the technology. So stabilized with a particular metal so that it does not get oxidized, and this amine with CO2 is stripped here, and here we operate it at near atmospheric pressure, so that the steam pressure here, what is used is very low, 2.4 kg pressure. So the CO2 is let out from this, which is cooled, and then through a cross-country pipeline it is taken to the soda ash plant. So it looks very simple, and the not many parameters need to be worried unless and until you don't have any good operators. This plant, even with a single man per shift, can be operated without any difficulty. So this is being now expanded to 1,200 tons per day. This plant is 175 tons per day. And this is the back filter, large back filter from the flue gas to take out all the dust and soda. And this column is a water column, and from here the gas goes into the carbonate column, and then goes into what you see is this is absorber. The tall column is absorber. So these are all the various circulation pumps. Here you can see that from the gas from this column is scrubbed so that no amine is wasted, and then the amine water is recycled into the system. And this is the stripper. This picture was taken when it was getting insulated for the second time because we had a weld repair. And this is the reboiler. Okay. And we had an independent cooling tower so that since this plant is away closer to the boiler, to limit the transport of the hot gases, we have, and also large volumes of flue gas, nearly 65,000 tons of 65,000 cubic meters of flue gas has to be brought. So in order to limit the sizes, etc., this was built closer to the boiler plant. You see, this is the boiler plant, and the gas is taken from the chimney. This is the interconnection from the chimney. This actually, these photographs, because this was presented to Niti Aayog, they wanted to learn more about what we have done in this carbon dioxide plant. So I will make a mention about SWRO plant, that is seawater RO plant, quickly, because why I thought it is necessary is this is also an innovation. Tuticorin area is water starved, even though Tamarabarni river is flowing and it is one of the perennial rivers of India. It also runs into problem because all the dams in that area, Srivaikuntam Dam, etc., Manimuttar, they run out of water during summer. And SPIC was forced to shut down their plant several times. And usually 40 to 50 days in a year, due to water starvation, the plant will be shut down. We thought, since now we have set up the CO2 plant and we are independent of SPIC, so we need not shut down our plant if we have access to water. So salt is produced by TAC. They have 400 acres of salt farms adjacent to the plant itself. Even today they are producing nearly 30,000 tons of salt. So, and we have seawater intake already permitted in 1989 itself. And they are taking the seawater, and seawater along with a little bit of brine, groundwater brine, and the salt is being produced. So we thought, why we cannot use this water in an RO plant, and then the RO rejects can be routed to the salt yard. We are not doing anything. This water is actually from the sea, it was going like this to the salt yard. Okay. So what we did, we introduced a control valve here, and then we brought it to a settling system, removed all the dust, etc., that comes with the seawater and goes through the RO plant, and then the RO reject, which is nearly 66% of the reject, will go straight into salt yard, so that it does two purposes. There is no loss of salt. In fact, it is enhanced because 33% of the water is taken out as good water, so it is a concentrate now. So our salt production also went up by 5,000 tons. Okay, so it helped us in two ways. And also we started getting water and we sized this RO system exactly to our water requirements so that even in the water shortage period, this plant is TAC plant can operate without issue. And in fact, government has requested us to keep operating this plant continuously so that the water is available for the other industries and also for the Tuticorin town. Okay, this is that settler system where the seawater is cleaned up, and this is the sand filters to take out all, if there is any further dust. Usually the water is very clean in Tuticorin Sea. And unfortunately, I don't have the side view. This is the front view. These are all the various membranes. This is a primary membrane where we produce the water up to 250. Conductivity is reduced to something similar to what nowadays are operating in the houses. Only thing, it is scaled up tremendously. It produces nearly 120 cubic meters per hour of good water. And this is for bringing it down, polishing the water down to almost to zero because it is used in the boiler. So we have two sets of membranes. And that finishes the my presentation. In case you have any questions or would like to know more about things, I am willing to give you the information and answer. If there is, otherwise you can send it through your HOD to me by email and I will send you the replies. Yes, sir. You want a honest answer or you want a technical answer? Honest answer is we don't incur anything extra. Okay. Only thing is instead of coal we switched over to biomass, right? So sometimes the cost of biomass is lower than that of coal on equivalent calorific value. Sometimes it is higher, but on an industry in a year it is more or less the same. But since biomass is being used by many people repeatedly nowadays, the cost is moving up. Unless and until there is an organized method of signing a year contract and then collecting it, etc., the cost of fuel can be a problem. Okay, we find that approximately 500 rupees per ton is the cost we are incurring nowadays. Additionally, had we used coal, because all other processes are remaining the same, right? We are not touching the soda ash technology. We are only how we produce carbon dioxide. So that is the only thing. So your answer is top of answer is the soda ash, green soda ash remains the same. Okay, number one. Then number two, if I use green ammonia, then it is tremendously costly. Okay, that is our point. We requested the Hindustan Lever not to insist on use of green ammonia because green ammonia today, to give you an example, is roughly around $1,300 per metric ton. Whereas normal ammonia is available for $540. The difference, even though it is not present in soda ash, there is no ammonia in soda ash. Okay, the entire ammonia goes as ammonium chloride. But still, we have to finance that extra cost. So we said that if you want us to use green ammonia, then the cost of soda ash will go up by roughly $300 per ton, which is approximately, which boils down to approximately 3 rupees per kilogram of detergent. Okay, which I thought it is very easy, can be passed on to customer, but their marketing department are not willing. So that is why we are not going into green soda ash, but we are stopping with 0.4, but still we are calling it the highly carbon reduced soda ash, which is sufficient for achieving their zero carbon footprint. Because it contains only 0.4 tons per ton, and then 25% of the detergent is soda ash, which is will bring it down to 0.1, hardly anything compared to what is found now.
I have a question.
Yes, sir.
You know, in primary amine always has a problem for CO2. It's used in industry extensively because they don't worry about carbon footprint. They have to recover CO2. And there is a loss of MEA, monoethanolamine. Whereas the trend now is to try secondary and tertiary amines. So did you try any mixture of amines so that your footprint and loss of MEA and footprint is reduced?
Yes, sir. What we use is, since my hands are tied with the technology transfer agreement, but I will tell you it is not ordinary amine. Okay, it is based on
proprietary
amine, and it is primary amine. And we did try several amines like monoethanol, diethanol, DMTP, so many, but the pyridine based is the best one. Okay, in terms of to tell you an example, if you use monoethanolamine, you will be using 3 tons of steam per ton of carbon dioxide required in the stripper. Whereas here we use only 1.2 tons. So that the economics of carbon dioxide completely, see, for example, the cost of production of carbon dioxide in using this primary amine, pyridine base, is only approximately, say, I'll tell you $50, not more than that, around $50. Whereas all other routes will be close to $100. What they are doing in US is $100.
Thank you.
See, the NPK fertilizer, that's what TAC is making, isn't it?
TAC is not making.
Not TAC, I'm sorry, SPIC. So, but when phosphoric acid is also produced there. So, about 30 years back, when the government said phosphoric acid can be imported, it was coming at a very lower rate. So, that was also a problem for SWIC to close down the plant. Is it...
Close down which plant?
The SWIC fertilizer plant, because phosphoric acid imported is available at a cheaper price.
No, I will explain to you. The SPIC is 2 divisions, or the 2 phases. Phase 1 is ammonia, urea, has nothing to do with the phosphoric acid. Phase 2, which the company is called Green Star now, due to various reasons it has been split into 2. Green Star produces, we import rock phosphate, we produce phosphoric acid, we import sulfur, we produce sulfuric acid. So rock phosphate and sulfur, we produce phosphoric acid. Phosphoric acid is converted into diammonium phosphate or other complex fertilizer, whatever is the market demands. Okay, we have 2 complex fertilizer plants. We upgraded the plant from 600 tons to 1,200 tons with introducing a spray technology. Okay, phosphoric acid became very cheap after Sterlite set up their plant, because Sterlite was producing when they calcine their copper ore, you get sulfuric acid, and they also imported rock phosphate and started producing phosphoric acid, and their phosphoric acid was cheaper for us to take from them rather than produce our own phosphoric acid. So we briefly shut down by having an understanding with Sterlite, taking their phosphoric acid. And we also set up our own phosphoric acid large plant in Jordan, okay, Indo-Jordan fertilizer. So we are getting acid from Jordan and also from Senegal. Okay, all those things are meaningless now because the phosphoric acid has become so high, cost has become so high. So we have taken our own mines on lease in the Middle East, and we bring the rock phosphate. We expanded the sulfuric acid capacity to 1,200 tons per day, whereas it was earlier it was only 100 tons a day. Now it is 1,200 tons a day, and we produce phosphoric acid nearly 800 tons a day. And also we are going to double it up now.
Thank you.
Phosphate mines are imported. Now in Middle East, sulfur also available. Why not you produce phosphoric acid from there and import? Won't it be...
Sir, we have a plant, sir, in Jordan. We have a 400 tons per day plant.
Of phosphoric acid?
Phosphoric acid.
Okay, thank you. Now, why not you are putting food grade? Now we are, most of the industry like Coromandel, all they use for the industrial purpose phosphate, but we are paying high cost of a food grade of phosphoric acid and importing from China. Why it is like that? Food grade phosphoric acid.
What we produce actually is food grade only, sir. So only thing is, you have to have the FSSI, so many things, other things, you should have a separate stream on instead of rubber lined equipment, stainless steel, those kind of things. So it can always be done, but in large plants, to operate a small plant, usually people don't show much interest. That is the reason. So that is why it is always, it is not part of the fertilizer plant. But it can be done. See, for example, to give you an example, SWIC built the aluminum chloride plant which is operating today even successfully, supplying to all the aluminum smelters in India to recover the fluorosilicic acid coming from the rock phosphate.
Sir, Tamil Nadu newsprint also using phosphoric acid. I don't know for what purpose, but my brother only imported from China and supplied. So what purpose in newsprint they use phosphoric acid?
Bleaching.
Okay. They can make in India, so why the unnecessary wastage of foreign exchange?
I think there is some. The only producer of food grade phosphoric acid is on this complex soda ash and ammonium chloride. Present technology.
I think giving our figure is meaningless because we convert the ammonium chloride to complex fertilizer. Okay. If you set up a new soda ash plant based on dual technology, it will be disaster because it will never make money because ammonium chloride cannot be sold in competition with urea because most of the countries they sell the urea on a subsidized rate. For example, cost of production of urea is 35,000 rupees a ton, whereas Government of India is selling at 5,250 rupees a ton, passing on the 30,000 rupees benefit to the farmer. So if I go and sell my ammonium chloride, which 25% nitrogen, whereas urea contains 46% nitrogen, farmer will say he will simply multiply by 25 by 46 and he will say, will you give it to me at 3,000 rupees. So whereas the ammonia content itself is 20,000 rupees in ammonium chloride. So unless and until you find a use for ammonium chloride, which is same ammonia value, it will be disaster. So you can set up only solvay plant, not dual plant. Solvay plant of 800 tons capacity, return on investment will be approximately 12%.
Sir was talking about application in detergent. Tamil Nadu product products is making clean energy and which is a promising input for a biodegradable detergents. So therefore, we had a very popular advertisement in the early 1990s. Washing powder Nirma, washing powder Nirma. So that coincides with the commissioning of the LAB plant in Tamil Nadu Petroleum Products Limited. If LAB is the most preferable and promising input for making biodegradable detergent, what would be the role of our product in the detergent applications?
It has two different areas, sir. The one is what is known as a builder. If you go into what is the manufacture of detergents, one is called a builder. Soda ash is a builder, whereas LAB, LAS, in fact, linear alkyl benzene sulfonate, because the LAB has to be sulfonated, and that sulfonate is the surfactant actually. One is hydrophilic, one is hydrophobic. So you need both to, because our Indian dirt, especially in Indian dirt, the type of composition what we use is, we have to have both the PO, EO based surfactant to take out the oil rich dirt which is mostly found in our Indian clothing. So Indian formulations are slightly different. So it is without the soda ash and without LAB we cannot make detergent. LAB contains around 11% and soda ash is around 25%. And I understand this is going to be a series of lectures, and this is the first one. So I wish you all the success. See that many more, and you people go rich with the knowledge you gain in these lectures. Thank you very much.
Put out the question so that we can either WhatsApp or mail to him and then get it clarified. Sir, really thank you for giving the inputs as for the students' knowledge. Right from the scratch you have started and you have given really very briefly and explained too good from the start to the recovery of carbon dioxide and other things. Thank you, sir. On behalf of students, can I put forth one question to you? It's not a question actually. Now that the students have gained theoretical knowledge, our students would be really willing to visit the industry. Yes or no, students? Yes. Will it be possible for our students to visit Tuticorin Alkalis? In case it's possible, kindly provide us that. Thanks a lot, sir.
Informative speech. Your insights on solid process and the CO2 recovery will prove to be useful to us in the years. The vote of thanks.
Esteemed speaker of today's session, Mr. G. Ramachandran, Tuticorin Alkalis, and Mr. A. Ramachandran, Ganga Chemicals, and many alumni and Vidya Shankar ma'am, faculty members and students. On behalf of Department of Chemical Engineering, it is an honor and heartfelt duty to extend our gratitude at the end of Dr. GSL lecture series in remembrance of Professor Dr. G.S. Lada, whose life, values and contribution have been the guiding inspirations for this gathering. So today's lecture is not only an academic platform, but a celebration of the ideals they cherished and the legacy they have left behind. Our sincere thanks goes to Mr. G. Ramachandran, who has given the most illuminating and thought-provoking lecture. Our sincere thanks goes to our department of head of the department for guiding us in a right path, and special thanks to Mrs. Vidya Shankar ma'am and other alumni who are here. We are grateful to that. And also we are thankful to our students, those who are all attended carefully and they have gained knowledge, I think so. In this gathering, most of the senior people have asked many questions, not from the student side. Anyway, we are handling, myself and Dr. Chitra ma'am is handling this course, Chemical Technology. So we are covering the soda ash portions. So we'll ask the questions from the students side and we'll convey to you, sir. Finally, let us carry forward the spirit of today's lecture, not only in the thought but also in the action, to inspire so that Dr. GSL's vision to comes for the generations furthermore. Thank you all for listening.
Hind, Gujarat, Maratha, Dravida, Utkala, Vanga, Vindhya, Himachala, Yamuna, Ganga, Uchchala, Daladi, Taranga. Tava Shubha Name Jahe, Tava Shubha Ashish Mahe, Gahe Tava Jaya Gada. Janagana Mangaladayaka Jaya He Bharat Bhagya Vidada Jaya He Jaya He Jaya He Jaya 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 He